Okay, this is the first order differential equations, and we will be talking about exact equations. Let's first talk about the exact differential form. So the differential form of function m dx plus n dy is said to be exact in a rectangle R if there is a function f of xy such that the partial derivative of f with respect to x is equal to m, and the partial derivative of f with respect to y is equal to n, these two functions up here. Now, the total differential of f satisfies this equation. So the derivative of f is equal to m dx plus n dy. And if this is an exact differential form, then this equation right here is called an exact equation. Okay, how do we test for exactness? Well, suppose the first partial derivatives, m and n, are continuous in a rectangle. Then m dx plus n dy is equal to 0 is an exact equation in R if and only if this compatibility condition holds true for all x and y in our rectangle R. So here we have the partial derivative of m with respect to y is equal to partial derivative of n with respect to x. Okay, so we will be taking the partial derivative of m here with respect to y and the partial derivative of n here with respect to x. I do want to point out that right here, this equation right here, let's write this. Any first order differential equation dy dx is equal to some function of xy can be written in this form. This is a differential form, and there are a variety of ways to do this. Okay, so this here, the compatibility condition, and this is actually sufficient for the differential form to be exact. A little more detail about this is there are two parts to the theorem. Exactness implies compatibility, and compatibility implies exactness. So we've seen that if the differential equation is exact, then both of these partial derivatives are simply the mixed second partials of a function f. Such their equality is ensured by the theorem of calculus that states mixed second partials are equal if they are continuous. Okay, so that is what guarantees this condition and that validates this equation. You know what? Let's jump right in and just try to solve this differential equation. Dy dx is equal to the opposite of 2xy squared plus 1 divided by 2x squared y. We will go ahead and write this in differential form, and we could have the opposite of 2x squared y dy is equal to 2xy squared plus 1 dx. We'll go ahead and put those in parentheses. So now we have 2xy squared plus 1 dx plus 2x squared y dy is equal to 0. Here we have our differential form. So now let's confirm the compatibility conditions. So as you can see here, we will take the partial derivative of m with respect to y, and that's going to be the partial derivative with respect to y of 2xy squared plus 1. And that's going to be equal to 4xy. Now, we'll take the partial derivative of n with respect to x. And of course, that's the partial derivative with respect to x of 2x squared y. And of course, that's equal to 4xy. And this confirms the compatibility conditions. Therefore, our equation is exact. So, if we have our differential form and it is exact, then the partial derivative of f with respect to x is equal to m. And we are going to integrate this equation with respect to x and come up with this equation. And here we will integrate m with respect to x. We will also go ahead and have this constant be a function of y. And this is because y is held fixed while integrating with respect to x here. And so our constant may depend on y. With respect to x. Okay. Continuing on, then to determine g of y, we will take the partial derivative with respect to y of both sides of this equation and substitute n in for the partial derivative of f with respect to y. And here, this is going to help us solve for g prime of y. We will then integrate g prime of y to come up with g of y up to a numerical constant, and substituting g of y into this equation will give us f of xy. And the solution to this exact equation is given, and this is implicitly given as f of xy is equal to a constant. Now, we are able to start with the partial derivative. So alternatively, we can start with this derivative. Partial derivative of f with respect to y is equal to n instead of this partial derivative of m with respect to x if we wanted. And then we would find by first integrating with respect to y. And we will see an example coming up. We will work an example like this. Okay. Okay, let's go ahead and look at our first example and put all of this together. Here we are going to solve this differential equation. And as you can see, we are in differential form. So you can see that this is m of xy and this is n of xy. And so now we have the partial derivative of m with respect to y is going to be, you can see that right here, the partial derivative of this m with respect to y is going to be 2x. And as you can see, that is going to be equal to, and we're going to have the partial derivative of n with respect to x, and that is also 2x. Whoops. That is also 2x, and that is the partial derivative of n with respect to x. Okay? And so we now have, therefore, our equation is exact. Okay, let me fix that. Okay, so now we're going to find f of xy, and we're going to go ahead and integrate m, and that is 2xy minus the secant squared of x dx, and then we are going to go ahead and have that plus g of y as our function that is also acting as our constant, which may not be a constant. Okay, so let's go ahead and integrate this m with respect to x, and we come up with x squared y minus the tan of x, plus we still have that g of y. So now we're going to go ahead and take the partial derivative of f with respect to y. And we will come up with n of xy. We're going to set that equal to n of xy. And that partial derivative with respect to y, which is here, is going to be just x squared. And we still have g of y. And so that is going to be the derivative of g, since we are taking the derivative with respect to y. And let's go ahead and have our n of xy, which is right here. Set that equal to x squared plus 2y. Therefore, you can see that g prime of y is equal to 2y. That leads us to g of y being equal to y squared. So now what we have, as you can see, what we now have is that f of xy is equal to x squared y minus the tan of x plus y squared. And the solution, therefore the solution to the exact equation is going to be given implicitly by, and we're going to have that x squared y minus the tan of x plus y squared is equal to c. Okay. Let's go ahead and try another example. As you can see, we are in differential form. And as you can see, here we have m, and here we have n. So you can see that this is equal to okay. So now we'll go ahead and take our partial derivative of m with respect to y, and we can see that that is equal to e to the x plus x e to the x. And as you can see very well, that is equal to the partial derivative of n with respect to x. Therefore, our equation is exact. Okay, so now we're going to go ahead and integrate n with respect to y and come up with f of x, y is equal to the integral of x e to the x plus 2 dy, and we're going to go ahead and use a function plus h of x. Now, you might be wondering why we found the partial derivative of n with respect to y instead of the partial derivative of m with respect to x. And what we want to look for is we want to look for which is easier to integrate. Is it easier to integrate m or n? And that's why we choose. And in this case, it's much easier to integrate n with respect to y. Okay, so let's go ahead and do that. So now when we find this integral, we have x e to the xy plus 2y plus h of x. And now we will take the partial derivative with respect to x and substitute for m. So let's take the partial derivative with respect to x of f, and we're going to set that equal to m this time. So that partial derivative of f, we're going to take the partial derivative here, is going to be e to the xy plus x e to the xy. Of course, that's our chain rule, plus h prime of x. And since we're taking the derivative with respect to x, of course, partial derivative with respect to x, the derivative of 2y is 0. And we're going to now set that equal to m, okay? And that is going to be 1 plus e to the xy plus x e to the xy. And you can see that right here. This is m, and this is n, okay? So now you can see clearly that h prime of x is equal to 1. So h of x is going to be equal to x. Therefore, f of xy is going to be x e to the xy plus 2y plus x. And of course, we got that from here. And the solution to the exact equation is given implicitly by x e to the xy plus 2y plus x equals a constant. I might add that here we can solve explicitly for y. Let's go ahead and do that. So we have x e to the xy plus 2y equals c minus x. Factoring a y out, we have x e to the x plus 2. Go ahead and just make this just a little smaller, move it up. So we have y is equal to c minus x divided by x e to the x plus 2. Okay, let's also make a note, a reminder. So using your decision, which procedure for finding, for finding f of x, y, we want to consider each integral, the integral of m with respect to x and n with respect to y. So we want to look at which one of those integrals is easier. And as you can see, the integral, of course, m, the integral of n was easier than integrating m. Okay. Okay. The next example says show that x plus 3x cubed sine of y dx plus x to the fourth cosine y dy equal to 0 is not exact, but that multiplying this equation by the factor x raised to the negative 1 power does yield an exact equation. So as you can see here, we have that m is equal to x plus 3x cubed sine of y, and we have that n is equal to x to the fourth cosine of y. And so if we have the partial derivative of m with respect to y, we would come up with 3x cubed cosine of y. But the partial derivative of n with respect to x is equal to 4x cubed cosine of y. And these are not equal. Let me just do that. Those are not equal. So the partial derivative of m with respect to y is not equal to the partial derivative of n with respect to x. So there we have shown that that equation is not exact. Therefore, the equation is not exact. And so let's go ahead and use what they've asked us to do. We're going to multiply this equation by x raised to the negative 1 power and go ahead and see if we can come up with an exact equation. Okay, so we're going to go ahead and take x to the negative 1. Go ahead and rewrite that. And here you can see that we have 1 plus 3x squared sine of y dx plus x cubed cosine of y dy is equal to 0. Now for this new equation, we have m is equal to 1 plus 3x squared sine of y, and we have n is x cubed cosine of y. So now you can see that the partial derivative of m with respect to, with respect to y is going to be equal to 3x squared cosine of y, and that is exactly equal to the partial derivative of n with respect to x. Therefore, this equation is exact. So now we'll go ahead and solve this equation. We will come up with a function f and set that equal to the integral of 1 plus 3x squared sine of y dx plus g of y. And here we have x plus x cubed sine of y plus g of y. And now we take the partial derivative of f with respect to y, and we're going to set that equal to n. So the partial derivative of f with respect to y is going to be 3x squared cosine of y, and setting that equal to n, plus g prime of y, and setting that equal to n here. We have x cubed cosine of y. And I made a mistake right here. This is just x cubed. Okay, so therefore, g prime of y is equal to 0, and g of y would just be a constant absorbed in our final solution. So therefore, f of xy is equal to x plus x cubed sine of y, and the solution is given implicitly by x plus x cubed sine of y is equal to c. So we'll go ahead and put here g of y is equal to a constant. And that would just get absorbed there. And that concludes this video.